Now we've seen how moving wires through a magnetic field end up acting as a source of electrical energy, effectively like a battery. This is something known as a motional or motion-related electromotive force. We've seen it in a very simple example. I'd like now to consider the general case. So I want to consider the general case of a motion-induced or motional electromotive force, EMF. And to make this a fully general consideration, what I want you to imagine is the presence of some magnetic field. Just for the purposes of illustration, I'm going to draw this magnetic field as pointing upward. It could actually point in any direction for the analysis that I'm going to carry forward. I won't be making any special assumptions about the direction of the magnetic field. But I do want to be able to sort of draw, a meaningful illustration here. So let me just imagine the magnetic field is pointing, straight here out of the board. Now what I'm also going to do is to include a loop that's in the process of moving. And this loop is going to have two ends through which I'm going to be thinking about generating my EMF. So there's going to be a minus side, which I will call A again, and a plus terminal. Let me redraw this here. I'm going to have a terminal I will call A, that will be my minus terminal, and a terminal I will call B, that will be my plus terminal. And then my loop is going to go through this magnetic field, maybe like so, in some kind of a shape, like that. And now I'm going to consider this thing moving, or it's going to be changing its shape in time. So I'm going to consider a specific time interval. I'll study the changes that occur over that interval. So there'll be a time interval delta t, and the shape of this thing then is going to change. Maybe it does something like this, where it's going to, have some slight change in its shape over some small time interval, where this is going to be my initial dl, say, right? Where, remember, if we follow the original path from A to B, that's how we're going to calculate the EMF from A to B, or the effective voltage from A to B. And so as I go from A to B, let me make the pathway look here a little bit better, a little more smooth, right? I'm going to divide it into a series of chunks here, which I will call dl. But what has happened, you see, is that over my time interval, this chunk has been carried to some new location, like so, right? Like that, where this vector then represents the effect of the velocity. So this is the velocity of that particular chunk times delta t. That's how far my chunk has then moved over in that time interval delta t. And so what's happened in here, as you can see, is I've changed the area of my loop. There's this new region in here that I'll kind of hatch out that's been swept out. That represents a change in the area of my loop. Okay, now let's try to evaluate quantitatively the EMF. How would this thing behave if I were to treat this like effectively as a battery, as a way of generating electrical power by moving this wire here through this magnetic field? Well, we know that the effective EMF we have associated here with our battery was equal to the voltage that we calculated going from point A to point B, which is equal, from our usual analyses. We haven't really introduced any new physics here yet. That's going to be the integral from A to B around this loop of the electric field inside the wires dotted with dl. Now, we know, and we've just said, that if this were a nearly ideal perfect conductor, that the electric field inside that nearly perfectly conducting wire is going to be equal to minus the velocity of each chunk of the wire crossed with the magnetic field to ensure that we've reached equilibrium of distribution of charges within our wire. That's dotted with dl. And immediately we have this nice little cancellation of the minus signs that occurs for us, keeping careful track of the signs. And finally, I want to relate it to my diagram and to this time interval delta t. I like this vector here for reasons you'll see in a moment. So I'm going to factor out a factor of 1 over delta t, and then simply replace that factor on the inside. So here on the inside, I'm integrating from a to b of v times delta t, then crossed with the magnetic field dot dl. So far, so good. We're coming now back to some vector identities that we're about to employ. We've used the equilibrium relation of a moving conductor in a magnetic field in our definition of how to calculate voltages and EMFs. So far, we've just used the physics that we know. We have this interesting expression that has a cross product and a dot product. Now that's something known as the triple product, and there's some important vector identities that go along with this. And the reason why I want to employ vector identities is that this way of expressing the EMF just comes directly from its definition. But now this is where the power of mathematics comes in. If I can rearrange this into other vector forms, those other forms may have different physical interpretations that I can then use to learn something about the behavior of this system. So let's see what we know about these vector identities. So this is a little side note for you. I want you to notice that if I do something like a cross product, A cross B dotted with C, right? That is what is known as a triple product, triple vector product. So again, this is a little side note we're making. And for a triple product like that, it has the following geometric interpretation. If I have my vector A, say, points this way, and vector B points that way, we know that the cross product of A and B, the geometric interpretation, is that it is something that is perpendicular to A and B, and the magnitude of that cross product, because of the appearance of that sign function, represents actually the area of this rhombus that is spanned by A and B. Now that area being perpendicular to A and B, here I'll kind of draw the perpendicular, is a very useful geometric construct in its own right, because if I then dot product it with a third vector C, the fact of that of A cross B being perpendicular to A times B, when I take the dot product with C and project with the cosine of theta, I'm actually getting the height now of this parallelepiped, and when I multiply the height of that parallelepiped by the area of its base, what I'm actually getting here is the volume of this object that is spanned, this parallelepiped that's described by the three vectors A, B, and C. So it actually has the interpretation of volume. Now the nice thing that one can prove about this is that this volume that I'm calculating, of course, shouldn't depend on the area of vectors that I choose, so long as I always choose a right-hand set. Right? Notice the way I've drawn this diagram. If I do A cross B with my right-hand rule, that normal vector kind of points along the same direction as C, so I get a positive answer in this case. That's how I know it is equal to the volume. Similarly, though, I could have computed that volume in two other ways. I could have taken B and C as the first vectors and taken this face and multiplied by the height then that A would project off of that base, and I would get a right-handed system actually if I did B cross C. Using my right-hand rule, you can see that that somewhat points in the direction of A. So if I take that and dot it with A, I'll get a positive answer, and it's nothing other than an independent manner of calculating the volume of this object. And the final combination that I could use then would be the other triple that I can take is C cross A, if you follow your right-hand rule, somewhat points in that direction of B. So this can also be done as C cross A dotted with B. A quick mnemonic way to remember these identities is to notice we've just done what's called a cyclic permutation. If you look at how I went from this form to this form, I've basically moved everybody backwards. I moved C backwards one notch, so it appeared here. I moved B backward one notch, so that it appeared first. And I moved A backward one notch, but it sort of fell off the end, so I put it back at the beginning, and there is A. Similarly, if I do that same kind of cyclic permutation, A would go back one position, C went back one position, and B went back one position, but again, we had to put it back out in front. So that's the triple product. So I actually have three independent ways that I can rewrite this expression for my EMF, and each of those is going to teach me something different about the physics of wires moving through magnetic field systems. So let's take a look at least one of these here. So this is going to equal, after my little side note, I'm continuing with my analysis up here, there's going to be a 1 over delta t here out in front, integral from A to B. And now, the way I want to do this is I want to think about this in the opposite direction. So I'm actually going to cycle everything not backwards one step, but forward one step. It accomplishes the same thing. So I'm going to go from this identity where B then, or say this identity, and go upwards. So C moves forward one space, A moves forward one space, and B then moves forward one space, but we run out of locations, so it comes back around front. So if I do that up here, then DL, which was on the front, is going to come in first. So I'm going to have then DL cross with what was in the first position was my V delta T. So there'll be V delta T. And that then has its dot product with B. So we now have a new mathematically equivalent expression, but it's rearranged a little bit. There's a little different emphasis now in the structure. It's magnetic field dotted with something. And we need to interpret physically what the something is, DL cross V delta T. For that, let's go back to our diagram. Here we have DL, right? That's this segment. This vector here is V delta T. And the cross product between those two, if you think about what that represents, that cross product represents an area. And what it is it's the area of this little patch, and this little patch is showing us how much area has changed, how much the area of the loop here has changed in my time interval delta t. And for each of these little DLs and V delta T's that I have, it's going to give me a full accounting of all of the changes in areas around my loop. There's just one caveat here that we have to keep in mind, which is remember that the cross product gives me a vector, and that vector then gives me a vector area, and I have to be very careful about the signs of my various areas. In this case, what I have is I have DL cross V delta T. And if I did DL here, take this DL and cross it with V delta T, notice I will get a downward directed vector. But if we think about the way we are circulating around this loop, going around this way, from right-hand rule number 2, the upward sense of area for our loop is the positive sense. So this DL times V delta T is effectively giving me a negative change in the area of my loop, right? DL here cross V delta T is downward, but the positive direction, the upward direction is the positive direction for areas. So what this is minus the a change in the area of my loop that occurs in time delta t. So then when I put the whole business together, you'll notice what's happening is I have 1 over delta t. I then have an integral or sum around my loop of all of the changes in area associated with each portion of my loop dotted with the magnetic field. So what this integral totals up to then is simply minus the change in the total magnetic flux within my loop. And I can rewrite that, of course, as minus the change in the flux in my loop with respect to time t. And so we can see now that what we've managed to calculate is that the EMF, this motional EMF, I'll write it as E sub m, due to the motion of my wires through that loop is actually equal to minus the time derivative of the magnetic flux through that loop. And that is that of course gives you your happy professor symbol, because that is a very powerful idea, right? It gives me the full general result that indeed the EMF I was calculating for my little moving loop example in the past is directly related to the changing in the magnetic flux, and that this is actually a very beautiful, very simple, compact mathematical result that happens to hold true in all cases in general.